So that then leads me to the next part of the talk. So how do we get over this? We need to use oxide thermoelectrics, A, because oxides are more common, but they're also the only materials that are stable in air at high temperatures. If you're going to work at high temperatures, you've got to have something that's stable in air. Oxides are the best one. You very rarely need oxidation protection, so there's less packaging costs. There are a huge number of trivalent, quadrivalent, and quintivalent oxides. So if you restrict yourself to quantivalent oxides, there's something like 10 to the fifth different compositions. We haven't explored many of those. Also, being oxides, they have high melting temperatures, and if you choose 800 or 1,000 degrees centigrade as being a typical temperature, it means that these will operate at lower homologous temperatures, just temperature divided by melt temperature. The other thing about oxides, unless you choose a fast ion conductor, the vast majority of oxides have very low diffusion coefficients. And there's some oxides where the diffusion rates are so low that even over geological periods, you still have metastable phases, for instance, in the thoria compounds, the zirconia compounds. And I think I've said the last one before. So that's the rationale for oxide thermoelectrics. What I want to present here is an argument for a particular class of compositions. I'm calling them natural superlattices. In the mineralogical literature, they're called polysomes, modular phases, or homologous series. Different names, the same thing. So let me give you an example. So imagine that you have two different crystal structures, A and B, different compositions. For instance, strontium oxide and strontium titanate, if you stack them together, depending on the relative number of strontium titanate blocks and the strontium oxide one, you get the so-called Ruddleston-Popper phases. These are well known in the electronic ceramic community. They have high dielectric constants in some cases. But let's take this to be, say, the strontium oxide and this to be the strontium titanate. We can stack them together, just a block of A and B, or we can interleave them. So in this case, this is A2B, so we have two layers, 2 unit cells of A, 1 unit cell of B, 2 unit cells of A, B, etc. Oops. And here's another composition. This is AB4. Now, in this case, it's very important to emphasize that the nanoscale spacing is determined by composition, not by processing. So it doesn't matter what temperature you take these to. If you have this composition, this will always have that natural superlattice structure. So we've done a little bit of work on one of these other natural superlattices. It's made up of zinc oxide and indium oxide. Zinc oxide because it's a semiconductor, or can be doped to be a semiconductor. Indium oxide because this particular system forms natural superlattices. Here's a diagram, a sketch of the crystal structure. It consists of N blocks of zinc oxide layers with 1 block of indium oxide. And that's repeated. And this is not fanciful. It exists. Here's a coherent TM image, aberration-corrected image, I should say. These are so you're looking down columns of atoms. You're looking into the material, and these are sheets of indium oxide. There's another one. And they're separated by, I think in this case, 19 layers of zinc oxide. We can identify that these brighter dots are columns of indium oxide, and the darker ones are zinc oxide. In fact, with today's aberration-corrected microscopes, you can then do Eales analysis. So you can do an Eales analysis of 3 atoms there, or a column of 3 atoms there. You see it has the characteristic indium peaks. And if you move off, you then see the characteristic zinc oxide peaks, which are here. So we know the indium is localized to a monolayer, or periodic arrangement of monolayers. So if you look at a phase diagram of these natural superlattice structures, this is the one for indium oxide, you find that over a certain composition range, and I'm doing it at high temperatures here, you see these line compounds. And each of these line compounds is a specific superlattice, specific spacing with different K values. The work I'm going to show you is of the ones in this region. What's interesting is that at very low concentration, so by the way, I'm sorry, this is zinc oxide, and we're at indium oxide. So as you add more indium oxide, the spacing becomes smaller and smaller. Above this composition, K equals 3, it's about 40% zinc, indium oxide, that you don't have any more superlattice structures. But it depends on temperature. And in principle, these lines would go down to absolute 0 in temperature, but the important point is that at high temperatures, these lines persist, and they're very stable. They self-assemble, so you just have to mix together the indium and the zinc, heat them up, and if you're in this particular compositional range, say you're this one here, K equals 7, if you're that composition, you will automatically get, after you've sintered and heat treated, you'll get this superlattice structure. So it's just superimposing some thermal conductivity data. In this case, materials made at, I'll just concentrate on the 1250 data. This is annealed 7 days at 1250. You see the thermal conductivity drops from pure zinc oxide. And then once you form the superlattice structures, the thermal conductivity is almost independent of composition. So let's return to this micrograph. Remember, these are just monolayers of indium oxide. So if you have these two-dimensional sheets, then you'd expect that there's going to be different electronic distributions perpendicular and parallel to the sheets, and similarly, this should affect the phonon distribution. So to get low thermal conductivity, in addition to any point scattering, you'd really like interfaces, very regularly spaced. And if the right spacing, you can get coherent X-ray scattering and phonon, not X-ray scattering, phonon scattering. And you can then get zone folding. So the first thing we expect to see, excuse me, all right, I've lost my way. You will also expect that you're going to get new vibrational modes. This is just a detail. You're going to get vibrational modes associated with atoms vibrating in this direction, and various other directions. And you're going to also get vibrational modes that are associated with this structure, this layered structure, as distinct from the individual compositions. So, of course, I was going to show you that. That's why I show it. So this is a comparison of the Raman spectra. So for pure zinc oxide, and as you add indium oxide all the way to indium oxide, and these are just regular Raman shifts all the way from 100 out to 750 wave numbers. What you'll notice, those at the back may not see it so clearly, is the zinc oxide peaks are very characteristic, but as you add indium oxide, you begin to see new vibrational modes. Similarly, if you start at indium oxide and add zinc oxide, you'll see that the indium oxide modes persist until a certain concentration of zinc oxide. But in this region here, this composition region here, you find, I've highlighted here, the vibrational modes that the two phases, remember these are just blocks, don't have. I'll spare you the details of the analysis, but if you now look at very low energy Raman scattering, and this is an example, as you add indium oxide to zinc oxide, you get the zinc oxide structure. And once you start forming superlattice, you see these very low wave number modes, and they're associated with vibrational modes associated with zone folding defined by these superlattice structures. So that's one of the explanations for the low thermal conductivity of these materials. We can also do some IR reflectance. And what we observe is that if we have compositions before lower indium than is required to form the superlattices, we get rather mundane IR reflectivities. But above that composition, these compositions, you see that there are additional modes, these two here, and they're associated, we believe, with plasmonic losses in the material. So what we believe, in fact, there is there are 2D electron gas associated with each of these interfaces. Now, we don't know if it's in the indium oxide or at the interface between the indium oxide and the zinc oxide. But this is prima facie evidence for that. Just to show you that over the superlattice regime, this is data for thermal conductivity I've already shown you, but this is Seebeck coefficient. Over this regime, where we form the superlattices, there's an almost linear increase, or decrease, I should say, the Seebeck coefficient with composition. This is not what we want to see, but that's what we observe. But what we do want to see is the figure of merit also increases with, so that's the black data points here. And as you increase as you decrease the distance between the indium oxide layers, then you see the figure of merit increases. It looks linear, but we obviously have to get more data than is obtained here. So this at least gives you some direction as to what to look for in this class of materials. So let me just say a few more words. So I've shown you this picture for conventional thermoelectrics. So I mentioned up to this value, these were all the old materials. They're made up of scarce and actually rather toxic materials. You don't really want to ingest tellurium or bismuth. Some of these other materials are very much more complicated, but they're really superlattice structures. And they have to be made in that way to get the high values. And of course, as I mentioned before, many of them melt. The oxide thermoelectrics have not had the attention that the conventional chalcogenide thermoelectrics have had, so there's much less data. This is some of the data. Actually, there's a very active Japanese national program in this area, and they discover these sodium cobalt oxide crystals. And they go up to about 800 degrees. And some of the zinc oxide materials I've been describing, other people have measured, and they get these sort of values. So they're not competitive with these yet in terms of ZT, but they're competitive in all the other, what I consider the most important regards. And as I said, some of these are already natural superlattice structures. Just to give you an illustration that there are many superlattice oxides that already exist. This sodium cobalt oxide is the one I mentioned before. So here we have a layer of sodium between cobalt oxide octahedra. And then this calcium cobalt oxide is a material that's been developed in China primarily. And this is a material that some of you may recognize because it dates back to the superconducting oxides. It has a very similar structure, these layered structures. And there are many other 1D and 3-dimensional structures that have this. So there's promise ahead, and these many opportunities yet to be explored. So you might say, well, it's all very well to make these nanostructures. You've convinced us you can make them by ceramic roots. You can make large pieces of them. But they're layered. So how do you connect current through a body? Well, it turns out this is a problem that is only recently being identified. So imagine this is your polycrystalline material. Each of these is an individual grain. And the black lines here are these indium oxide layers. So what do you want? These nanosheets, if you like, introduce two anisotropies. There's an anisotropy in the thermal conductive in the two directions. So it's much lower in the direction of the C direction than in the A direction. That can be expressed in terms of an anisotropy factor and what the effective thermal conductivity of a bulk material is in terms of these aspect ratios. You can also use the same formulation to describe the electrical conductivity of this polycrystalline material. And the interesting thing is these layers act as short circuit shunts. So grain boundary is much less effective in these materials as far as electron transport. And I've already mentioned these are stable structures.